Josh has got us all. We are all being held lovingly in Josh's hands. Yeah, I love you all. All right. So, God, I've streamlined this a couple of times. What did we even do last time? What did we do on Monday? I don't even remember.
We did a bunch of limits.
Limits, okay, thank God, that's been done. No more limits. So, yeah, the limits are done. This is a classic part of Calc 2. I think you're gonna like it, because in the end it will come down to not doing, I hate to say it, that you'll like it because it doesn't involve integration, but that's the truth. It kind of does, so it'll be a lot of setting up integrals. And that's really where the art of this all comes in. So we're gonna start talking about volumes of solids, of revolution. It's a lot of ums. But it's really cool and fun. And if you like to visualize 3D things, you are, and I know at least a couple folks in here do. You're gonna love this. So here's our plan. Here's our goal. So I'm gonna be given a curve, y equals f of x, and I've got a range on it, so x is between a and b, and when I draw this, anytime I draw a function, I think it always looks like this, like when it's the yield arbitrary function. B. And y equals f of x. What we want to imagine, we're going to do two different imaginings. The first one is we're going to spin this around the x-axis. So we're going to rotate this thing around the x-axis, and it's going to form a solid. We want the volume of that solid. So let's picture this. So spin the curve around about, this looks like drunken writing, but it's pretty sober for the most part right now. So the curve about the x-axis. And find the volume of the resulting solid. So literally just everything I just said slowly and spelled poorly. Cool. So sometimes the fun part of this is just figuring out what the thing looks like. This one's not too bad. Spin this around. You get a shape that looks like this. So this end's going to be flat because it's just cut right there. And then it kind of comes back like this, and then out like this, and it's like flange, kind of a flange, like this. You can't really see that part behind there. Here's the axis of rotation.
How?
Hold on, let's show you it in just a little.
It's like a lamp. Yeah.
Does this make sense or no?
Like if you take the little paper lanterns and like make a circle with it, that's how I think about it.
Yeah, that's a really good way to think of it. Yeah, so or like a plant stand or something like that.
Are you using the dotted lines?
They're the ends. So I'm rotating. So this is the surface, right? So this is the outer part.
Yeah.
And these are where I'm cutting it. So this is flat right here and here. So when I spin those, this is just a flat part. This looks really weird, demented. Kind of looks a little bit better like that. So let me show you a couple other angles. The bottom of this thing looks like this. So if I was looking at this from the bottom, it's just a flat thing. It's kind of a bottom view here. So this is underneath, and it's just totally flat. And it's this line, God, I gotta calm down. My axes are really bad, but this is like the under view of this thing.
Oh, okay.
It'll hopefully become a little bit better as we move through and practice this a little bit more. Well, let's practice a few right now. What if I took this shape here, and nobody say it out loud, but let's just, if I took this from 1 to say 5, and spun that around the x-axis, what is the resulting solid? We'll just start out chill, right? We'll build
Is it a square?
not a square, because it's rotated.
Cylinder.
Or cylinder.
Cylinder, yeah, right, so here it is. Oh, here we go. What is the locus of points touched by this pen? It's a cylinder. And what if I tilt it?
Cone?
Yeah, a cone. It's like a frustrum is the technical term, so a frustrum of a cone. You like do this and you get like, there's a tiny top and then straight edges. So this is like Lampshade City, right? And I'm rotating it. So this one would actually be like this. But then I'm like kind of changing its orientation.
Volcanic.
Yeah. Yeah, like a really, like a volcano or a space capsule or something like that. So sometimes that will be the hard part. What the hell does this thing look like? So gosh, that's fun. Boy, those drawings look weird. But we're gonna find the volume of that. And guess how we're gonna do it? We're gonna cut this thing up into little rectangles, spin the rectangles, see what that looks like, and then let there be infinite rectangles. What a shocker, because that's how we do everything in here, right? So let's derive the formula quickly. I'm going to cut this up into n equal pieces. So I'm going to partition this, x naught, x1, x2, all the way out to x of n. I'm going to pick a representative in each interval, in each sub-interval. And I'm going to call that x sub I star. And it can be any point inside there. Is this story sounding familiar? This is like a bedtime story for us, right? Hopefully, I guess a morning time story sounds better. I don't want everybody blacking out after this. And then we're going to use that to determine the height of the rectangle. So I come up from there. Good God, I'm really having trouble today. And so the height of that rectangle is going to be determined by the point that I pick. So the height of that rectangle is going to be f of x sub I star. That's the height of that little element. And then I'm just going to put elements all the way through here, and I'm going to basically approximate this thing here with a bunch of rectangles, and it's going to look like this. More or less, right? And maybe even a super thin one here to kind of get that flanging effect. So I'm going to approximate this shape with a bunch of rectangles. And I'm going to spin those rectangles. What is that going to look like when I spin these?
Stairs.
Wait, what?
Just like stacked discs.
Stacked discs, and what were you saying, Lou?
Stairs.
Yeah, like circular stairs that lead up to the top of a stage, right? So, yeah, maybe, or a fountain that has round stairs that come up. So they could absolutely be stairs. But I guess I was thinking what Kitra was saying there in like stacked coins. And let me keep my orientations safe here. So got that first one, just turns into a disc. And then the next one turns into a disc. And so on and so forth. So the next one looks like a much thicker disc. So let's see, so there's the front of it, and then it's like super thick, like that. And then you get the point, right? Birthday cake.
Yeah.
Birthday cake. That's what it is. I'm really hungry, so that sounds fantastic. Nice vegan birthday cake. All right, so what I'm going to do is add up all these volumes. So this would be our approximate volume. What we need to do is figure out a formula for the volume of each one of these little discs. So let's put on our formula volume hat, volume formulas hat, and let's think about a single one of these discs. So first off, how thick do you think I'm going to call this? What is the thickness we always say here?
Change of n.
Change of x, yeah, change of x, yeah, delta x. So the thickness of this thing is going to be delta x, and we'll say sub I because it might change depending on which of those we're going to be in. What is the radius of this disk right here? Well, it's just the height of the function, right? So the height of the function is what determined the height of that little rectangle, and that's what determines our radius. So this radius, r, is equal to f at x sub I star. What is the volume of a disk like that? What is it? Let's kind of get this like this and call it r, and then height h. What's the volume of that thing? Of a coin of radius r, height h. What's the area of the top? Pi r squared, beautiful. So when you have a nice homogeneous shape like this, like all the slices are the same, all you need is the area of that slice times the height, and this works for anything. So the volume of this thing is going to be pi r squared h. Like just think of this, if I had like a weird little like star pattern like this, had some kind of weird star thing, and I told you the area was 7, and then I told you, oh, I'm just extruding this like a Play-Doh fuzzy pumper or whatever. Do they make those little Play-Doh pumpers where you put the Play-Doh in the pump and you push down on the handle and like it extrudes it? Yeah, so like, let's say I got one of those, and I know that the area of that is 7, and that the height of this is 11, then the volume of this is just the height, the base area times the height, cubic units. So that's what I'm doing here. I'm taking the area of this top times the height. And so the volume of this thing, the ith volume, the ith little disk here, the ith layer of the cake, the math cake, is pi radius squared times its thickness, delta x sub I. And I'm just going to add those all up. So the approximate volume, we're going faster every time. Approximate volume is equal to the sum, as I goes from 1 to n, of pi f of x sub I star squared delta x sub I. And now I'm just going to let n go to infinity. What happens to that? Somebody help me out here. Have you seen this enough to remember where this goes? What does the sum sign turn into? Integral, beautiful. And it's an integral from where I started, which would have been a to b, so it's over the range. I had that up there at one point. Well, pi stays pi. What does this all become? We know the i's and the stars all go away. What does the delta x become? That's the dx, beautiful. You're rocking it, Olivia, so you got that, so yeah. And then this xi star just becomes x. So you were really, really right there on the cusp of it. That's it. That's our volume formula. So the volume of a curve, f of x from a to b, spun around the x-axis is this formula right here. That's it. So let's do an example. Let's put that formula up. See, now I said we're going to get done in an hour today, so I'm going to try to keep to that. So, example. Let's start off really chill. F of x is x squared. Really nice. And let's say our range of x is from 1 to, oh no, let's go from 0 up to 2. Nothing crazy, just ye old parabola from 0 to 2. So let's say there's 2. 1. I'm going to spin that around the x-axis. So spin around the x-axis. What's the volume? So let's just use the formula. volume equals. You can bring that pi out in front. That would probably be a better plan. So bring the pi out in front. Integral over the range of slices, 0 to 2. The function is x squared, and I'm going to square it. Dx. If I was saying just set this up, you'd be done. And we could do this. I don't want to waste a bunch of time doing, right? Goes to x to the 4th. Then when you integrate 1/5 x to the 5th, plug in the 2's and shit and all that. Yeah. So we could do this pretty easy. So we're not going to. We're just going to set up volumes today. Does that sound okay? Let's talk about something a little more interesting. Let's make this more fun. Constantly more and more fun. Unbelievable, but true. What if I've got some curve, that's f of x, but underneath it I've got g of x. And I really am just interested in this region between these two being spun around the x-axis, and I want that value. I do see some furrowed brows. And if you're trying to picture it, well, let's see. It looks a lot like that lampshade before on the outside. Yeah, so the outside's still kind of that same shape, but the inside would be all hollow. And then there'd be a big hole down here in the end. So there'd be a big opening down here, big opening in the front. Actually, this would be a little thicker, wouldn't it? There's kind of a, because there's kind of a straight edge right there. So this starts like this. Can you see that? It's weird. It's got like a little digestive tract or something, you know, like little intestines kind of working through some sort of primordial creature blipping its way through the protoplasm. Little jellyfish consuming things, excreting things. Good story, Dr. T. So, okay. So what's the volume of that? So what would be, like, just like using this one formula, how could I do it? If I had to do in 2 computations, yeah, Kidra, what would you do?
Don't you just find the volume of each one and subtract them?
Yeah, totally. So you find the volume of this inside part subtracted from the volume of this outside part. So beautiful, perfect. Let's write that up. So for this one, the volume, and I'm going to put this in kind of a different way, that's going to help us think about it. It's going to be the outer, so pi is going to be in front, but it's going to be the outer curve squared minus the inner curve squared. And I actually do ask you to write it like this because it's going to help thinking. Outer minus inner, it's going to be a theme here. And let's even make this more precise. This is also the outer radius. And this is the inner radius. It might help sometimes to think of that as a radius. So, let's do one. Let's take the inner, let's see, so we've got square root x squared and the square root of x. They meet right at 1. What does it look like when I spin it around the x-axis? It's hard to explain in words in some ways, right? What does the outside look like, though? Just think about this, right? Without that there. When you spin that shape, when you spin this shape around, what do you get? Yeah, like a hemisphere. Yeah, right. Yeah, like it's not quite because it's a parabola, right? But it does look like a gumdrop. Right? Do people still eat gumdrops, or is that just some fucking old man thing that only I know anymore? Okay, all right, I'm still kicking. So the outside looks like kind of a gumdrop or Pac-Man ghost or something like that. Now that's old, but you still know who Pac-Man is. All right, so that's the outside, but what about the inside? What does the inside look like?
Yeah.
What's that? Air? There's air.
Uh-huh.
What shape is the air?
Ellipse.
It's like this, but like in a circle.
Thank you.
Yeah, like a cross, right? So like the cross section kind of looks like this, right? So it's weird inside there, right? It like goes down to a really sharp point. Like it's like a little bowl. It looks like a trumpet, like the inside of a trumpet that's sealed off at the end. So just think about that. That's what we're removing. We're removing a trumpet from it. Yeah? No? Yeah. No, no. Good news, you don't have to picture it to find its volume. What is the volume? Your turn. Can you set up the integral for the volume? This is 1. 0. You don't need anything else. Some folks some folks just really can't do these visualizations. It's just like, I think different people's brains work in different ways. So if you can't, just smile and laugh and think, well, I got lots of other things I can
The outer
do.
curve, square root.
Yes, yes it is, Lou. Yep, and that's good. That's a really good question to ask. What is the outer and what is the inner? Yeah, Kelby.
Are we setting or solving?
Just setting it up. Yeah, please. Today's just setting up. Because if we start doing integrals, we'll get like 3 done and it'll be the end of our time. So. We'll write that. Forget the pie. That's all we need, is to be able to just set up. Kelby, yes?
Would you simplify?
Yeah, I probably would. Turn it into something pretty like that. Absolutely. And then that'll make integration really lovely, right? Just power rule. We harken back to the days when integrals were simple and just power rules. Any other questions on this, friends? So I'm gonna push it just a little bit more. Yo.
Can you explain why x squared is the outer?
So we're spinning around this axis here. So think about, as you do that, what is going to be on the outside, right? As you're moving, what is furthest away from this axis? The square root of x function. So that's the outside. So like you can think of it this way, whichever thing is furthest from the axis of rotation is your outside. Is that a good way to think of it?
Yeah.
Okay, awesome. Yeah, because if you can't visualize it easily, then I can see why outer and inner might. So we can change this to furthest distance to closest distance. It'll also work. So if you're having trouble visualizing, that might be a good mnemonic for doing it. So is this still, Olivia, is this feeling a little bit better? Okay, awesome. Any other questions, friends? Cool. Let's spin it around something besides the damn x-axis. So, about spinning about other horizontal axes. I don't even know, axes? Yeah, not axi. Okay, so, I don't even know if I should draw a picture on this as opposed to just doing examples. So let's just do some examples. Let's start off with something simple. Let's take y equals x squared. So just x squared, that's my shape. I'm gonna go from 0 to 1. Nothing fancy. and I'm gonna spin this thing around different axes and get different shapes. So we're thinking horizontal axes all the time, so it's always rotation like this. The other thing we're gonna do is spin around vertical axes, but that's a different approach. So let's say I wanted to spin this around y equals -2. So about, and let's come up with different formulas over here. Y equals -2. So we're still going to use the same furthest and closest formula. So let's write the formula up again. Volume is pi integral of our range of slices. And here we're going to have furthest. And that's going to be a formula. Furthest distance squared minus closest distance squared. Or, and for me, outer and inner works better, so whatever works best for you. Okay, so when we come to this, we're spinning this. What is this thing going to look like? Let's try that. Let's play that game first. You spin this little wedge around there. Imagine it. Just see if you can imagine it floating through space and coming down and sweeping out a solid as it comes down this way. What does that shape look like?
I don't know.
Yeah, it's hard to explain, right? Like you can do, yeah, but that's, yeah, there's like, and to me it looks like a gasket, kind of like a little gasket or a washer of a very particular type. So you've got this large rim, so this piece here, and this radius here is going to be how far? How far is that tip to there? Well, wait, we're just 2 units, right? So this is y equals -2, and then the distance from this tip down to here is 2 units. Oh, sorry, yeah. I didn't think I was being clear about what I said. So that's actually 2 right there, and this is all open space, right? This is all just wide open. And then you've got a flat interior wall, so I've kind of got this flat thing on the inside, and then on the outside I've got this flanging. It kind of happens like this. And then on the inside, it's just like a little cylinder cut out of it in some ways. It's not the best drawing. Yeah, I don't really know. Let's see. Let's try to see like this. Maybe I can draw it better like that. Oh, that's better. So it looks like that. And then these walls here are just flat. There's a big hole right in the center. So to me, that looks like a gasket. It doesn't matter.
Stump,
What's that?
stump or a
Stump.
lamp post.
Yeah, exactly. Yeah, that's hollow, right? That's also, like I bored out the center of it. Yeah, yeah.
Like one of those fire starter techniques.
Oh, yeah, yeah, yeah. Yeah, I like that.
So the space, the 2 units of space, that's the brim of the hat, basically?
Yeah,
Okay.
yeah. Like we could fit like this on some sort of, like a metal rod or something. We could like insert this if the metal rod had a radius of 2. This could just fit right onto it. Maybe like the base of a lamp or something like that. I think that's probably just getting too weird. Let's just do the formula. Because look, we don't have to understand at all what we're doing to use the formula. Where do your slices run? From 0 to 1. Now, here you gotta be careful. What is your outer radius? So it's this distance plus this distance here. So like for an arbitrary x, and you might wanna do this like for yourself, for an arbitrary x, how far is that? Well, it's this 2 units plus x squared, right? So this little distance here is x squared. And then I add 2 to it. So the outer radius is 2 plus x squared. So my outer radius is 2 plus x squared. And then I square that. That is my outer radius. What is my inner radius?
Just x squared. No?
Nope. What is the closest? So come here. So check this out, Lou. And this is the bottom, right? That's the bottom of my shape.
2.
Just 2.
So
Just two?
Just 2, it's constantly 2 from the axis to the bottom of the shape.
Okay.
Does that make sense? Anybody need me to explain that more? Inner radius? You're good, or yes, more, explain more?
One more. Yeah,
One more? Okay, so here's where I'm spinning it around, Fernando, yeah? Here's the bottom of the shape that I'm spinning, so check this out. My finger's the bottom, why am I using my finger? This is perfectly straight. So how far is this pen from the axis of rotation? It's always just 2 units. And this is my inner curve. So this is the inner curve, and this is the outer one. This is the closer one, that's the further away from. Does that make sense? Here's another way to think of it. If that geometric way I'm talking about it is bad, you can always just do top equation minus bottom equation. So check this out, that's gonna work, the top equation. So let's do the outer. For the outer, the top equation is x squared, and the bottom is -2. So I put x squared minus y equals -2. That just gives me x plus 2. The inner one, the equation, this is y equals 0 minus -2 just gives me plus 2. But in the end, it's just that distance. So there's so many different ways to think about this, but this is our formula right here. Tired, but doing it. Let's try it. Yes, Kelby.
Can you do one that has 2 different, like the one on the left side, but then it also has like that space that you're talking about?
Totally sympathetic.
Okay.
That's exactly where I was going. Let's do this one. The old wing of a bee. A bumblebee wing, or a bumblebee pin. Just who I am. Should just bubble it out constantly. So let's do this around y equals -7. That doesn't look like y equals -7, but who gives a shit? It is. Imagine. Here, make it. What's the volume? You got a picture. Who's the furthest? Who's the closest? And then I'm going to set another one up here for you to do right after that. And I'm going to put a curve, I'm going to make the axis on top. So I'm really twisting it up. And so for the next one, do it around y equals 3. This is y equals -7. Then do it for y equals 3. And that'll kind of stretch your mind a little bit. Haven't done one where it's on top yet, so that's like, it's gonna look different. Trust your gut. Think about the geometry if you can. Still recording here. I started thinking about all our friends who have not arrived at class yet today. Thinking about you, whoever you are. Cassie. Yes.
So will we ever rotate it around a point that lies in the center?
No, that would be a mess.
Okay.
So Kitra is just asking if we would ever drive it through the center, that would just be like,
Cause I was like, if you do it, it makes like overlapping. so
yeah,
it'd be-
it sounds painful.
Just generally no.
Just generally no.
Okay, cool.
Yeah, it is cool. It sounds like a fun thing to think about. Maybe not even a fun thing to think about, but a messy thing to think about. Yeah. We'll start getting this one together. So for this one, that's my outer. That's my inner. So for this around 7, it's always top minus bottom, and that's important when you get over to that one, because the top is now the axis. So for this one, top is square root of x minus negative 7. That's this distance here. In other words, it's this distance, square root of x, plus this distance, 7. But if you always think top minus bottom, you can't screw it up. And it takes care of the sign, squared, minus, now the inner, top is x squared, minus the bottom, negative 7 squared dx. So if you're simplifying, this is just square root of x plus 7 squared minus x squared plus 7 squared. Could simplify if we wanted, but this is like Calc 1, right? This is just like Calc 1 problems, just like FOIL that shit out. You doing all right, Fernanda?
Yeah.
Okay, cool, okay, all right, good. So, let's try this one. Spend a few moments on that. I'll come around and check and see what's going on. Let's see what we got. Beautiful drawings. That's a little weird. Yeah, let's see, so is this your, so you're not doing top minus bottom. This would end up working out okay, but it's not officially right, because who's actually on the top there?
Oh, it's square x.
So the 3 is on top. So here, when we go around this one, the top is actually the 3, so. Mm-hmm.
Okay.
Yeah. You notice you're squaring them, so in the end, it's not gonna matter, but like for setup purposes, it could matter. It could matter. Good over here. Oh, yeah. Oh. What's going on, David?
Good.
Yeah, it's just smoke. Beautiful. Nice drawings there. That is not right. That is backwards, actually. So it should be the top curve is a 3 minus, and then the outer curve is the x. Oh wait, I might have actually told a couple people they were right about something when they weren't. Let's do this one together, just to check. So when I spin around this one, who is the outer now? It's the x squared, right? So we gotta be really careful with that. I think I might have told someone that the square root was right for that. But now when I go around this, the outer becomes the x squared. So the volume here is gonna be pi over the range of slices. And then I'm gonna do outer radius. So the outer radius, and I'm still gonna do top minus bottom, so it's 3 minus x squared. That's that distance. That is literally, if this height here is x squared, and this height here is 3, that distance is 3 minus x squared. And I'm gonna square that minus, this is my inner here, when I'm spinning around that one. So inner and outer switch when we move the axis above. So then your inner radius is gonna be top 3 minus the curve where it ends, squared like that. Do you want me to explain that again, Kelby?
Well,
Yeah.
I don't understand why when you're going about -7 as the y, that the 7's on the right side basically, and now it's on the left.
Because I'm doing, so I'm always going, and I would, this top minus bottom to keep signs straight. So I'm always doing whoever's on top minus the bottom. So here, when I was going around the 7, these two were on top.
Okay.
Does that make sense?
Yep.
Awesome. Huzzah. So if you like, this isn't too bad, right? This is actually in some ways, like there's no calculus going on, really. Not yet. The calculus is waiting in the why do I think lobby? I don't even know. Well, I think calculus is waiting in the lobby for you, sure. Okay. Got one more thing to show you today. This is going to be our practice. We're going to be doing this. Like in the next exam, I'm going to give you a bunch. I'm going to give you like a shape like this and say, set up the integrals for around this. And then I'm going to say around this and around this. We haven't done that yet, so let's do that. So here, in these last ones, I want to make this note. In these, our slices were perpendicular to our axis of rotation. Our slices, when we set up the Riemann sum, are perpendicular to the axis of rotation. We had horizontal axes, and our slices were vertical, so they are perpendicular. What we're going to do now is where the slices are parallel to them. So let me, maybe I can erase, is it okay if I erase here? Yeah. Okay, just check with everybody. All right, cool. So now let's do our slices. And now for this one, instead of top minus bottom, we're going to do right minus left always. So I'm going to keep these two together. Now we'll rotate around vertical axes. So these are all going to be x equals something, where the x coordinate is constant. And our slices are parallel. That's the symbol for parallel. That's the perpendicular symbol. Parallel to our axis. So in other words, start off with the chill. X squared. Take this region. Let's do the simple thing first, just around the y-axis. So that's going to look like a cup with a straight outside and a parabolic inside. So it's like a hollow cup. You see that? Yeah. All right, so what we're going to do is we're going to take each element. Here's how you think about it. This is why Riemann sums are important, because they help us develop formulas. And that's really what I'm trying to get across here, the power of this method of thinking. So we're going to take this element here, and we're going to spin it around the y-axis. What will that look like? Bless you. So let's see, let's label. So it's delta x thick. It's f of x sub I star high. It's at x sub I star. What is the shape of this black rectangle if I move it around the vertical axis? What is this shape? Like a cylinder, like a can, right? So it's just a shell. So these things before were discs and washers. These are shells, cylindrical shells. So when I spin that thing around, what I get is something that looks like this. It looks like a tin can. We just have to figure out what the volume of that tin can is. And then we're going to add up all these volumes, and then we're going to let the number of things go to infinity, and we're going to formula it. So, the thickness of this can is delta x. I'm going to make this so much less painful than it will be. If you go look this up in a calc book, it's very, very painful, the way they do it. I'm going to do it more intuitive, derivation that I think makes a lot of sense. So this thing is delta x thick. Its radius is x sub I star. So it's literally the x coordinate. Check it out here. The radius of this can is the x coordinate of the slice. So whatever that x coordinate, yeah, does that make sense? So this is x sub I star, because that's usually what we say is where our rectangle is located. So I'm gonna call that x sub I star for my radius. How high is this thing? Let's actually call this f of x. How high is this can?
F of x sub I.
Beautiful, yep. Yep, right, it's the function. It's the height of the function at that x sub I star, yeah, beautiful. 2 people at once saying it, that's freaking awesome. Very exciting. So now we just gotta come up with a formula for a tin can of thickness delta x, radius x sub I star, and height f of x sub I star. So here's how we'll do it. Let's cut that sucker open on the side. So I'm gonna slice it right here, and I'm going to unfurl it. So uncurl it. So I'm gonna slice this here, and it's gonna turn into a strip of metal. A 3D strip of metal. Can you imagine that? Like cutting this can, like take a soup can, take the bottom off, cut it down the side and unwrap it.
Ooh.
Yes, yeah, thank you. Ah. Where's my coin? I think Kelby just earned it.
No, you can keep it.
Oh shit, I don't know where it is anyway.
I'm never gonna use it.
You don't want change?
No.
Yeah, I don't either.
You can Venmo me. It's okay.
It's okay, all right, good. All right, so, how high is this metal strip? How tall is it? Beautiful. Yep. Yeah, f of x sub I star. Yeah, that's solid. How thick is it? Delta x. Now here's the tricky question. How long is it?
XI.
What was that?
No, wait. That's wrong.
So careful, so here's what we did. We took a circle. So this is the top view now, right? So I took a circle of radius. Well, let's say, what if it was a circle of radius r? What is the
Oh,
perimeter?
it's 2 pi r.
2 pi r.
2 pi xi.
Yeah.
2 pi xi.
We're both ready for a break. Absolutely.
Yes.
So, yeah, so the circumference of a circle is 2 pi r. So that's equal to the circumference of a circle of radius r. And since our radius is just our x coordinate, this thing here is 2 pi x sub I star. And what's its volume then? This is the ith volume. What's the volume of that strip? How do I find the volume of a rectangular prism? Just multiply all the dimensions together, right? Yeah. So I'm just going to multiply base times width times height. And what I'm going to get is 2 pi x sub I star times f of x sub I star. And I'm going to save that little delta x for the end, and we know why. We know why that goes at the end. So that's just the ith volume. So this thing here is going to look like a bunch of little cans. It's like, take a roll of paper, right? Like you got a roll of paper, like you put in like a register or something like that, push it down. And it looks like a bunch of little cylinders all stacked together, right? So if you extrude one of those things, that's what this would look like, kind of. That's what all these things are gonna look like. So I never thought of that before, but that's nice. So our approximate volume is the sum of all these. So approximate volume is equal to the sum.
It's like a toy lightsaber.
Yeah, exactly. Or those crazy ass canes I've been seeing on TikTok. People have these canes that are like this big, and then they like, and it's like this big.
Oh yeah.
And they must be super shitty canes. They like act like you can beat somebody's ass with them, but you know they'd fold around anybody's head. And just like... So these things, we're gonna add all these up. And this should be delta x of I star, or delta x of I, excuse me. Oh boy, that's the hard part, because like when we let number of cuts go to infinity, so letting n go to infinity to get precise, integral sign from a to b, 2 pi, let's bring that sucker out front. X of I just turns into x, f of x dx. That's our formula. Not the kind of thing you just guess, right? Like, so using these Riemann sums gave us incredible intuition to developing that true volume formula. And I'm gonna make it look a little bit different. So this is like just around the y-axis, but you know we're gonna do different axes. So, in general, here's the mnemonic way to do it. In general, the volume will equal 2 pi integral over your range. This is going to be your slice radius. So this is going to be like x plus or minus a constant, or a constant plus or minus x. This is going to be something like that. And then here it's going to be top curve minus bottom dx. The slice radius is going to be right minus left always. This needs a little explanation, but this will come together in just a second. So let me show you how to do this in general. Okay, so example. Rotate our fine volume formula. Rotate this shape. Let's just do y equals x squared. No, let's do this one here. Square root of x squared from 0 to 1. So let's do that little shape, because that's got a nice, easily defined. You can see who's the top and the bottom in the formula. It still shows up. About. First, let's do the y-axis. So here's my tip. Draw an arbitrary slice. Vertical slice. This method, you really want to have that vertical slice drawn. So I'm just going to like draw a little slice, and then I'm going to label it. It's just x. And label it x. Because that's going to help us figure out the radius of the shells. So having that is like kind of an anchor, a mental anchor. So I'm going to spin this around the y-axis. So I'm going to go to my volume formula. Volume is 2 pi. I picture that I have shells, so I know it's this volume formula. Or I remember that this slice is parallel to my axis, and I know to use this formula. So you have to figure out which formula to use when. So 2 pi, and then it says my slice radius. Well, here's the radius right here. It's x minus 0. So just x, it's just the x coordinate. So this is my slice radius. Times the height of my function, which is just top minus bottom. Done. That'll give the volume. And that's pretty crazy. It's ridiculously simple. I feel like Kidra, you were thinking, that looks simple. Were you thinking that? I have to say yeah.
Sure.
Sure, thanks. I thought you were. So really nice and simple. So let's do it around another one, because I've got like 5 minutes, and I promised Kelby we'd be out of here by 3. And I do not break my promises to Kelby. Except that day you left after you were like, is it gonna be okay? The minute you walked out, I said, I cannot believe
They
she
told
left.
me.
Okay.
Yeah.
But it was just, it's just me being an idiot. So, they told you. So,
So I still feel bad about it.
no, come on, just stop. If you want $1? You want $1?
No.
No, I was like, that's not gonna help, I can't
No.
buy you off, okay. Alright, so let's do it around x equals 2. So about x equals 2. Now watch how lovely and simple this is. So I erased my lovely mnemonic, hopefully you wrote it down, but we'll go through it again. So I'm going around x equals 2, I noticed that, it's right here, I noticed that is parallel to my elements, so I use this formula. So I go volume equals 2 pi integral from start to finish. Notice this, it's just the range of the stuff that you're spinning. It's not like the range to the axis or anything. So be sure, because this is a really common error, this range of integration just covers the slices. Where are your slices running from to? And then here I'm going to have my radius. And I'm going to use right minus left. So what is the distance here? That's why I have this arbitrary element drawn. What is the distance between x equals 2 and this arbitrary x slice? So between 2 and this x slice, how far is that? 2 minus x, beautiful, exactly. So this is just 2 minus x, and then the height is just top minus bottom. That's it, done. We have 2 minutes left. Now I would like you to do the same thing. Take the shape and rotate it around x equals -5. So set up a formula for the volume, rotating about x equals -5. I'll put the mnemonic up here because we're just starting out today. Sometimes your slice will be on the right, sometimes your axis will be on the right. You're always right minus left. I think that clock is like a minute fast. Kill me. I know.
Nobody's promise.
Yes, Lou.
If it's right till wave,
Right minus left.
wave. Oh, yeah, I have that.
So you have, okay, good. Yeah, yeah.
Isn't it 8x squared minus
minus bottom. So that'll always be the case, Vivian. You'll always have that top minus bottom for this one anyway. What else? And I saw Kelby, you were like looking
No,
at that
I'm good
with
now.
suspicion. Okay, all right. Awesome. That's it. Get out of here. Leave. That's it. Josh, thank you.